Good afternoon, everyone. This is Mr. Couple. I'm here today with my IBSL Year 2 students, and we are going to be learning about the greenhouse effect. The three main ideas for today's lesson they're right here. So it says the greenhouse effect prevents the Earth from being a frozen ball of ice. So we talked about that in our last lesson, how we did the calculation. I actually found out that I made a mistake in that calculation. I used the 1400 for the power, but I should have used the surface one that we calculated, the 245. So we actually got a much higher answer than it should have been, but whatever. The second thing I want to talk about is how ultraviolet and long wave infrared radiations are absorbed by the atmosphere, but visible light gets through. And then lastly, we want to discuss how humans are enhancing the natural greenhouse effect, which is causing global temperatures to rise. And you've probably heard of that. It's called climate change. And you guys know about that. We did a whole project on it. Okay, so first let's talk about this is interesting. So the moon and the Earth, the moon goes around the Earth. We're about the same distance from the sun as the moon is. I mean, the same average distance. If the moon is going around the Earth, then the average distance between the moon and the sun is the same as the average distance between the Earth and the moon. I mean, the Earth and the sun. So sometimes the moon is a little bit closer to the sun than the Earth, but other times the moon is further away. So on average, we're the same distance away. So realize that when looking at this picture here, the distance from the Earth to the sun, so I should zoom in on that. The distance from the Earth to the sun is going to determine how hot the Earth can be, like how much power is radiated. We talked about that last time. So the intensity is equal to the power output of the sun divided by 4 pi d squared, where d is the distance the planet is away from the sun. And so you can see that as you get further and further from the sun, like out to where Jupiter is at this much further distance, the intensity of the sunlight at Jupiter is going to be much lower than the intensity at the Earth. But the moon and the Earth are roughly the same distance away. So the intensity of the solar radiation on the moon and the Earth will be the same, roughly. But then here's what's weird. We do not have the same average temperature as the moon. So the moon has an average temperature of 255 Kelvin. So if you want to convert that into Celsius, we just have to subtract 273. Let me load my calculator. So if I take 255 minus 273, we get negative 18 Celsius. And then if we do the same thing for the Earth's temperature, so 290 minus 273, we get 17 degrees Celsius. So the average temperature on Earth is 17 degrees Celsius, but the average temperature on the moon is way below zero. So what's the discrepancy here? Like, what are your thoughts on this, you guys? Like, we're the same energy source from the sun. We're the same distance away from it, Earth and moon. Why is the Earth warmer than the moon?
Because the moon doesn't have an atmosphere?
Yeah, it's exactly right. So the moon has no atmosphere, but the Earth does. So it's this atmosphere around the Earth. It's kind of like a blanket, and it retains some of our heat, and it allows us to stay warmer than we would have been otherwise. Good job. So this is called the greenhouse effect, and the greenhouse effect is the reason you're alive. If it wasn't for the greenhouse effect, the Earth would be just as cold as the moon. We would be frozen. You wouldn't have any life on this planet if that was the case. You'd be kind of like Mars, or it's like this frozen ball. So let's talk briefly about the greenhouse effect. I'm sure you guys have heard of this before. So the way the greenhouse effect works is you have this solar radiation coming in from the sun. We can see it on this diagram here. And then that radiation is going to pass through the Earth's atmosphere. Well, not all of it does. Some of it gets reflected off the atmosphere. And then even still, some of it also gets reflected off the Earth's surface. We talked about that last time when we discussed the albedo. But for the most part, a good chunk of this is going to get through to the Earth's surface, and that's going to heat up the Earth. It's going to be transferring energy to the Earth. Now, as the Earth warms up, it's going to act like a black body, and because of its temperature, it is going to release its own radiation out into space. And so that's what you see going on in this part of the diagram down here. So there's the energy leaving the Earth. That's the Earth radiating like a black body. Remember that equation was the power is equal to the emissivity times the Stefan-Boltzmann constant times the surface area times temperature to the fourth power. And so if you increase the temperature of the object, you'll increase the power that the object emits. So the idea is like the temperature that we have on Earth, the temperature of the Earth, is set based on the incoming power. So what has to happen is there needs to be a relative balance between the amount of energy that's coming in and the energy that's coming out. There has to be a balance. Usually I should write that with power because we always talk about it with power. And so we need to have this balance of what's coming in versus what's coming out, and that'll allow the Earth to have a constant temperature. And so that's what we were talking about last time when we did that calculation of what the Earth's constant temperature should be. Okay, but this picture is a lot more complicated, so I'll zoom in on this part here. This is the part that we're really interested in. So what happens is that not all this energy doesn't just freely exit the Earth, because what actually happens is because of the atmosphere, some of that energy is going to get absorbed by the atmosphere. Now, this is energy from photons. This is light. This is light that the Earth is releasing out like a black body would. And so some of that energy actually ends up coming back to the Earth because it's being absorbed and then re-emitted by the atmosphere. And so that very clearly, like this part here, this is the greenhouse effect. The fact that not all the heat is able to escape the Earth. I shouldn't say heat. I should say solar radiation. Not all the solar radiation is able to escape because some of it gets absorbed by the atmosphere. Just like on the way in, some of it got absorbed by the atmosphere. On the way out, some of it is also going to get absorbed by the atmosphere. All right, let's look at these. These are the culprits. These are the reasons why we are able to live on this planet and not be frozen. It's because of these four. These are the four main. You guys know what these are called? I bet you know the names. What are these gases called?
Greenhouse gases?
The
These
green.
are these are the greenhouse gases. And know them and love them, but not too much because climate change is also caused by these guys. But if it wasn't for these greenhouse gases, the Earth would be a frozen ball of ice. So the greenhouse gases are carbon dioxide, methane, water vapor, and nitrous oxide. And we're going to talk a lot about these guys today. There's a whole lot of science I want to go into on this, but just for now, just realize that these are the four main contributing gases that cause this warming effect called the greenhouse effect. And you guys you've experienced the greenhouse effect because it also happens with glass. So what happens is like imagine you have a car like parked outside on a hot day, and you walk away from the car and then you come back and it's like super hot inside the car. Well, the same thing was happening. It was like the sunlight, the visible light, was able to pass into your car, but then all that heat gets trapped in the car. The car starts to try to radiate some of its energy out, but it can't go through the glass. The glass ends up keeping it and retaining it inside because the glass absorbs that light. And so it's sort of a similar idea to that what's going on just across the atmosphere. Okay, there are two types of greenhouse effects that you need to know about. It's important to distinguish between these two greenhouse effects. So one of them is the natural greenhouse effect. So that's the one that I've been talking about. The other is called the enhanced greenhouse effect. And this is what's causing climate change. The enhanced greenhouse effect is leading to climate change. Let's begin by just discussing the natural greenhouse effect. So the natural greenhouse effect happens because these greenhouse gases we just talked about, carbon dioxide, nitrous oxide, methane, water vapor, they're naturally present in the Earth's atmosphere. I mean, their atmosphere is just filled with these things. It's about 1% of the Earth's atmosphere is filled with greenhouse gases. And they're there just naturally, just due to naturally caused things. And this is nice because it keeps the Earth from being frozen. Like that's why we exist. Now, the enhanced greenhouse effect is problematic because what's happening is due to human activities, like power generation and various farming techniques and things like that, we are dumping extra amounts of greenhouse gases, taking them out of the earth, like where they were trapped beneath the earth, and we're actually adding them out into the atmosphere. So we're increasing the concentration of these gases in the atmosphere. And what that's doing is it's causing less of the radiation to escape the earth. And so the Earth is retaining more of its radiation, which ends up increasing the average temperature across the Earth. So this is a major problem if we're not careful to fix it. And as you guys know, like that's what we spent like months talking about in the group 4. What questions you guys have for me about distinguishing between these two greenhouse effects? So I think it's important that you realize that the greenhouse effect isn't necessarily a bad thing. It's a bad thing if we let it get out of control. If we let it run away, then it could be bad.
So we need it in small amounts
Precisely.
to maintain our temperature.
Exactly right. Yep. And if not, we would liquid water wouldn't be able to exist on this planet. I want you guys to look at this chart. I pulled this out of the Cambridge IB textbook. So here are the 4 greenhouse gases. So we got water vapor in particular, oxygen. Um, what else is there? Wait, isn't that carbon dioxide? That's wrong. That's supposed to be carbon dioxide. CO2. Fix your textbook, guys. And then methane and nitrous oxide. So let's just look at this real quick. This is listing you natural sources and then anthropogenic sources. So anthropogenic, does anyone know what that means?
Created by humans?
Yes, that's created by humans. So I want you guys to just look at this for a minute, kind of look at both sides, and then just shout out anything interesting that you noticed.
For the CH4, it comes from like wetlands and oceans. Why don't we get like a lot of water from wetlands?
What do you mean by water from
Like
wetlands?
H2O, the greenhouse gas, like the H2O. It's
Oh,
like,
well, so this is like I'm sure you heard of like swamp gases. So like there's just gaseous like outgassings from the swamp are going up into the atmosphere. So this is like the methane is in the atmosphere. So it's not like the water on the earth we're talking about. We're talking about actual evaporated water that's up in the atmosphere. Does that make sense?
gotcha. Yeah, gotcha.
There you go. So it's important to realize that, even if humans did nothing, like if humans weren't here, these gases would still be in the atmosphere. They're natural. But human activity is enhancing or increasing the concentration of these gases in the atmosphere. And then that's causing a problem because that's raising the global average temperature. It's kind of redundant to say that, but the average temperature of the Earth means it's global. But just in case, emphasizing that it's a global average because there can be some places that are hot and in other places that are cold, but the average temperature will be increasing. So you'll still have the coldest days of the year, like those will still exist, but the average temperature across the globe is going to increase. All right, so check this out. What happens when sunlight passes through the atmosphere? So you imagine like we've got the sun here shooting out all this radiation towards us, sunlight, and then that sunlight's going to hit the Earth's atmosphere, and then what happens? So this chart, this graph is a really good scientific data showing you what happens. So the yellow is the sunlight without the atmospheric absorption. So that's like what we receive at the top of the atmosphere. And then the red is what we receive at the Earth, at the surface of the Earth. And so what you'll notice is, first of all, the what was I trying to say? What's it called? The amplitude, like the height that it reaches, is way lowered. Like you can see it here. Like the intensity is dramatically reduced when it goes through the atmosphere. It's just like if you're looking at something through sunglasses, things are going to be dimmer. I mean, that makes sense that the atmosphere would do that. But now, what you have to pay attention to on this chart, like let's look over here. This is the ultraviolet part of the spectrum. So this is UV. So I'm looking over here at the ultraviolet. You'll notice that there is a point here. I'm going to draw a line like this. Okay, so look, the highest frequency that, or I should say the shortest wavelength that reaches the Earth is there. But actually, the shortest wavelength that the sun releases is actually over there. So you'll notice that there's this whole entire band right here of light that does not reach the surface of the Earth, which means there's something in the atmosphere that's blocking that or absorbing it or preventing it from reaching the ground. And you'll notice those gaps all over the place. So there's another gap here. There's another gap here. And you'll even notice like these miniature dips like here and here. And so that's what's important about this diagram, is noticing that not all the light from the sun can make it through the atmosphere, that there's a lot of wavelengths of light that actually get absorbed by the atmosphere. And that's what we need to look at in order to understand the greenhouse effect. What questions do you guys have for me about this graph? Cool. Now, do you notice any dips in the visible? Like any major significant dips where there's nothing getting through? So are there any visible wavelengths that do not make it through the atmosphere?
There's that one by 750, and isn't that right at the end of the visible spectrum?
There's a little dip here, but I mean, for the most part, it's getting through, right? It's
The one on the far left. It's a dramatic dip.
Sure, but that's also because the black body also itself dips down. Like that's the ideal black body. So even the black body itself is dipping down there. So that's what's I would say that's what's causing that dip. But the idea is like there aren't any wavelengths of visible light that get blocked. They all make it through. But there are wavelengths of infrared and wavelengths of ultraviolet that are getting blocked. That's what's important to realize, that there are significant gaps in the infrared and in the ultraviolet, but there are no gaps in the visible.
Well, because if there were, we wouldn't be able to see those colors that got blocked.
Yeah, precisely. And then our eyes probably would have evolved in some other part of the spectrum to be able to see. So yeah. Okay, so let's talk about what's going on. Let's talk about this dip. So I want to talk about the ultraviolet blockage. So photons in the ultraviolet region have enough energy that they actually can break bonds within gas molecules. So ultraviolet has really high energy. So ultraviolet is high energy photons. And so these photons have so much energy that when they come in and they whack into oxygen in the Earth's atmosphere, they can actually break the oxygen apart. So you can see that oxygen is splitting into two separate particles. So normally, oxygen is two atoms stuck together. It's O2. It's a diatomic gas. So the photon can come in and it actually can like provide energy to rip these guys apart. Then those loose oxygens can go team up with another pair of two oxygens to form ozone. And the ozone is really helpful to us because it creates even more blockage of UV. I mean, that's a good thing. It's a good thing that there's this gap in the UV there. That's a good thing because otherwise there'd be a lot higher rates of skin cancer and things like that, because ultraviolet light has so much energy that it can actually cause cancer. Like it can break apart bonds between atoms. So that's just so ozone production is one example, but there's lots of gases that get ionized in the atmosphere because of the exposure to these ultraviolet. And so that's what you're seeing there is like there's this big gap there of ultraviolet that can't make it to the Earth's surface. But what about these infrared gaps? Like what's going on there? All right, first, before we get to that, I want to talk about the gases in the atmosphere. So here's a pie chart showing you the percentage makeup of the gases in the atmosphere. So you can see that by far, the Earth's atmosphere is predominantly made of nitrogen and oxygen. And if you look at the chemical structures, I should say the molecular structure of nitrogen and oxygen, you'll notice that they're diatomic gases, like oxygen and nitrogen, which consist of two molecules, and they're very tightly packed together. They're super tightly bound, and they don't absorb energy from sunlight. So there's very little contribution to these normal gases to the absorption spectrum. So none of these holes or gaps and stuff like that are caused by nitrogen and oxygen. They're caused by other stuff. And I guess technically you could say that it's oxygen here, but it's yeah. Okay, so let's compare these molecules to the greenhouse gases. So what do you notice about the shape of the greenhouse gases compared to the nitrogen and oxygen? What do you guys see there? Thoughts?
There are multiple molecule structures.
Exactly. They got much more complicated structures with like these pieces like hanging off from that center part. And you can see that in all of these guys. And it's this geometry, I don't know what to call it, this architecture, who knows, this shape that's causing these to be greenhouse gases. And so I want to talk more about this. So these guys are loosely bound and they absorb energy from sunlight. They vibrate like springs. So when they absorb energy from the sunlight actually drives them into oscillating like a spring. So here's a water molecule, and I have this cool video that I can show you guys. There's a fancy chemistry speak for this called like degrees of freedom. But you can see like this water molecule is flying by, and notice that those molecules on the edge are like vibrating in and out as it goes past. And so it's that vibrational energy that we're really concerned with here. And so realize that, what is light? It's an electromagnetic wave. We'll just draw a crappy electromagnetic wave here. And so if you have a particle like oxygen where it's made of charged particles, I should say a molecule made of charged particles, the electric field, which is what what electromagnetic waves is really made of, this electric field. The electric field can actually apply like an external force that'll like drive the molecules. It'll like make them start to move and vibrate and oscillate around. And so these electromagnetic waves can actually stimulate or excite these particles. whereas it can't do that to these molecules up here. Like they're too tightly packed together. But when you have these loose hanging parts, they can actually like set into these vibrational, what we call vibrational modes. So here are some images of the vibrational modes of carbon dioxide. So this one up here does not contribute to its greenhouse gasness, but these ones do. So these are the ones that cause the greenhouse gas nature. So you can see that there's like this anti-symmetrical stretching. This one is symmetrical. So that's not what sunlight does to carbon dioxide. But sunlight does these other three things to it. So these are what we call the natural modes. So like these are like the ways that carbon dioxide, I'm just focusing on carbon dioxide. These are the different ways that carbon dioxide can oscillate or vibrate. So it can do that, like one's going in while the other one's going out. So it does like, I can't even do that with my hands. It's too hard. It's like trying to play a piano. The other modes are like oscillating like this. And then the last one is like these big, large scale stretching. So you can see there's all these different like vibrational spring-like oscillations that this particle can undergo between these bonds between the atoms within the molecules. So if the frequency of the sunlight coming in like that, if the frequency of the light matches the frequency of those oscillations, then it can reinforce and it'll actually the light will get absorbed. So like it'll get absorbed and it'll set the molecule, it'll drive it into those oscillations. So the result is that the light gets absorbed by the molecule. There we go.
So it's like the waves. If there's two waves that are at the exactly the same, it'll increase the intensity.
Yeah, so it's kind of like resonance in a sense. But I mean, more importantly though, what's happening is like you're pushing like the energy is it's absorbing energy and it's raising it up to a higher energy level. So when it's not oscillating, it's just hanging out down here like normal. But then when you absorb the energy, now these particles are oscillating, like they're moving around. I'm trying to show that they're excited. So it gets excited, and so now they're moving around. But they don't like to be excited. Like that's not the preferred energy level. They want to be at a lower energy level. And so what will happen is it's going to then drop back down again. This is very similar to the Bohr model idea. I mean, this is a universal idea in physics. If you raise something up to a higher energy level, it's going to fall back down again eventually. And so that's what's happening is like the sunlight. So this is actually the sunlight that's providing this energy to excite these molecules and to drive them into these different oscillations. It turns out for carbon dioxide that these vibrations occur at these wavelengths. And so you might remember from waves that c, the wave speed, is equal to lambda f. So if you have the wavelengths, it's akin to having the frequency, since this is just the speed of light. We usually give it in wavelength, but realize that that's really a frequency. So if I give you a wavelength of light, there's also a corresponding frequency that goes with that. And so it just so turns out that light that has these wavelengths, 2.7 micrometers, 4.3 micrometers, and 15 micrometers, if sunlight has that exact frequency, that wavelength rather, it will cause the molecules to vibrate at the frequency that's natural for them. And so that it'll get absorbed by those molecules. And so this is a graph showing you the absorption of carbon dioxide based on the wavelength. And so you can see there's just these huge spikes here, this huge spike here, and then these smaller spikes there of where carbon dioxide absorbs light. And so if we compare this back up to the previous chart up here, that's too far away. I'll just go to this one down here. So if we look at the 2 to 6 micrometer, so I'm going to show you guys this chart here. So this is the opacity of the atmosphere. So this is the absorption. Is actually used by astronomers to figure out where's the best place to put our telescope. What kind of light are we looking at? Where should we put our telescope? So if you look in the range of 2 to 6 micrometers, so let's go find out where 2 to 6 micrometers are. So it looks like it's in this range here, from here to here. Then you notice that giant spike right there, like that. That's absolutely caused. Whoops, I did the wrong spike. That's caused by carbon dioxide. So that spike in the opacity or the absorption is caused by carbon dioxide. And you'll notice that there's a visible window here. So for visible light coming in, there's a window. This is kind of like the opposite of the other graph I was showing you guys. So this is the absorption. This is the amount that gets absorbed. So in here, gamma rays, X-rays, ultraviolet, all that stuff gets absorbed by the atmosphere. None of it gets through. But then visible light can get through. And then radio waves easily get through. Like radio waves don't have any trouble. But then over here, like this is the infrared spectrum. It doesn't get through at all. And then where we are is, so that anyway, but that's the idea is like these different spikes that you see here are caused by the different greenhouse gases. So look at this graph. This is a better graph to look at. So we're going to zoom in on this range here from 1 to 10. Guess I missed there. 10 is over here. So if we zoom in on that 1 to 10 range, which is where the action's happening, then you can actually see exactly which greenhouse gases are causing those absorption spikes. Now I hated trying to plan this because no one could agree on what graph to do. So this is showing you the transmittance. So on this graph, the higher up it is, the more it gets through, and the lower it is, the less it gets through. So this is more like the first one I showed you guys. So that's that big gap here where no light is transmitting through. And so it's saying that that's because of water vapor. And so every time you see like a little bloop, that's caused by carbon dioxide, and then another bloop, that's caused by carbon dioxide. So you can go in there and you can look and see what greenhouse gases are causing the light to get absorbed. Hopefully that makes sense. This is pretty confusing stuff. So every greenhouse gas causes absorption at a specific wavelength of light. Okay, let's bring this home now. So we're ready to do this. Okay, so here's a diagram. Okay, so we've got the Earth's surface here, and the Earth is radiating in the infrared part of the spectrum because of if we think about the Wien's displacement law, we talked about the maximum wavelength. It's like lambda max times T equals, I don't remember the constant stuff. Just call it constant. But so there's that maximum wavelength that you're going to emit at based on your temperature. And for Earth, the lambda max is in the infrared. So that's what the Earth is releasing. So the Earth is giving off infrared radiation. But it just so happens that infrared is exactly the wavelength that greenhouse gases do what? No.
Like absorb energy or heat?
There you go. They absorb it. And so this light comes in and it gets absorbed by those greenhouse gases. It excites the greenhouse gases. They get raised up to that higher energy level, but that's not a natural energy level. So eventually they're going to fall back down. And when they fall back down, they end up re-emitting those photons. Those photons get re-emitted by the molecule, but they get emitted in random directions. They get emitted in every direction. And then you'll notice that some of those photons, some of that light ends up coming back down to the Earth. And so the overall result then is that not all that light was able to make it out, because some of it got sent back towards the planet. And then that's what's causing an extra energy input to the Earth, which raises the temperature up from that frozen state that it should be in, and it raises it up. So it's a good thing. But then you can imagine that if we thicken this cloud, so if this cloud gets thicker, if we pump more greenhouse gases up into the atmosphere, then the amount that gets absorbed is going to increase even more. And so that is a problem, because that will cause more and more energy, more and more light energy to come back down to the planet, and that will cause global temperatures to increase. Okay, this is the last diagram that we need to look at. I'm trying to see how much time I have here. I don't remember what time I started, but I'm sure that we're about out of time here. So this is the big picture of everything. So this is called the Earth energy balance. And so let's just kind of walk through this and then we'll be done. So here's our incoming solar radiation. So that's the sunlight coming in. You'll notice that some of it gets absorbed by the atmosphere. Just like we said, on the way in it gets absorbed. It also gets absorbed on the way out. Where's the absorbed? So here's the absorbed on the way out. Now you notice that way less of it gets absorbed on the way in, because the sun doesn't have a peak in the infrared. It peaks in the visible. And so there's less infrared available to be absorbed on the way in, because the atmosphere absorbs in the infrared. Okay, then you can see there's some reflected by clouds. There's some reflected by the surface, and that's the albedo, and then that stuff goes back out. So that means that we have a total of 161 absorbed on the surface. So what is that going to do to the Earth? Well, it's going to cause the Earth to heat up. And so the Earth will be warmed by this energy, but the Earth then will release its own energy, and that's what we see coming over here for the surface radiation. So now the Earth is going to release 396. That gets absorbed. Some of it gets through. Some of the light passes through what's called the atmospheric window. It can pass through. It doesn't get absorbed, but most of it does get absorbed because infrared is the sweet spot for absorption. And then what happens after that is some of it gets emitted out, which is good. That goes out to space, but then some of it comes back in again. And so what happens is if you do all the math here, if you add everything up, you'll find that you end up getting a 0. So like if you take like the total that's coming in, so let's look at this. So 341 coming in minus the 102 should be equal to the outgoing over here. Does that work? I don't know. Looks like it works. There you go. And so that means, so there's a total balance in this case. So we have a balance of energy where the amount of energy that comes in is equal to the amount of energy that comes out. I shouldn't say energy, this is power, but anyway, the amount that comes in is equal to the amount that comes out. And so what happens if the in is equal to the out? You end up having a constant temperature. But then what happens, so you can see that the greenhouse gases are are reducing the amount that comes out. And so that means that we're increasing the in. And so what has to happen is if that increases, then the whole system is going to have to change. And so what will happen is because of the Stefan-Boltzmann Law, if the temperature of the Earth it were to increase because more of this energy is being sent back down to the surface, then that means that the power that we release is also going to increase. And you'll end up creating this new equilibrium at a higher temperature. And so that's what we're worried about with the greenhouse gases, with the enhanced greenhouse effect, is that we're worried that we're increasing the amount of energy that's coming back down from those greenhouse gases, re-emitting the energy back to the Earth, that we're going to increase that amount, and that's going to cause the temperature of the Earth to increase and then to reach this new equilibrium. But you're always going to have this energy equilibrium. It's just a natural consequence of what must happen as a result of the Stefan-Boltzmann equation. Okay, do you guys have any questions before I stop recording?
Not really, but when is the assignment going to be posted?
I'll post it right after I upload the video. There's 3
Alright.
questions that I'm going to have you guys answer. Pretty simple stuff.
Alright.
Okay, have a great day, guys.